In question 14, the equation we have in y1 is the square root of 4 minus x squared, and then we have, following that, 1.5 times y1, 2 times y1, 3 times y1, and 4 times y1 of x. And what we want to look at is, let me get a pen and I can write again. Hang on. First of all, I have already set up my viewing window for the correct minimum and maximum values for x and for y. So pressing graph, we want to make a prediction or an observation about what the coefficients, the 1.5, the 2, the 3, and the 4, what does that change about the graph? So there's my first curve, the square root of 4 minus x squared. There's 1.5 times that curve. There's 2 times that function. 3 times that function. And 4 times that function. Now what I see there is a graph that's getting taller every time. The x-intercepts at -2 and +2 haven't changed. But what is changing is the graph gets taller, and I think we need to kind of talk about how much taller. And if you look, let me just grab this and get it down where I can maybe write on it. I'm not sure I'm going to be able to do that. Let's see. Yes. Okay. I'll take that out in a minute. But if you look at that, am I going to be able to draw on that? Yes. Okay, good. This last one that was graphed crosses the y-axis at 1, 2, 3, 4, 5, 6, 7, 8. There's a y-intercept at 8. The initial curve has a y-intercept at 2. Alright, and that is the graph of 4 times the square root. 2 times 4 gives you 8. So what I see there when I'm looking at that graph is I'm seeing a curve that is 4 times as tall as the initial curve. And if we look, see if I can highlight that curve. It's crossing the y-axis at 1, 2, 3, 4. So the curve that has a y-intercept at 4 is actually this graph. And the initial y-intercept is 2. If you multiply that by this coefficient 2, you get 4. So let me clean this up a little bit. Ooh. Now I really want this to go away, so we'll cut it out. Okay. What I think I'm seeing is that multiplying by 1.5 makes the graph 1.5 times as tall. Multiplying by 2 stretches the graph out so it's twice as tall. Multiplying by 3 stretches the graph out so it's 3 times as tall. And multiplying by 4 stretches your graph out so that it's 4 times as tall. So I think that we have a vertical stretch by a factor of 1.5, 2, 3, or 4, depending on which one we're looking at. Okay, so now back to the calculator. If I change the initial function to be the square root of just x plus 1, then the equation that I have then in y2 is 1.5 times the square root of x plus 1. And then I've got 2 times the square root of x plus 1, 3 times the square root of x plus 1, and 4 times the square root of x plus 1. So what we're looking for now as we graph this is, do we think we see the same vertical stretch by a factor of 1.5? 2, 3, or 4. So there's the initial curve. There's 1.5 times the initial function. 2. Okay, now if I pause, I think I paused. There we go. If I pause that graph right here, the initial curve, you can kind of see where my pointer is. The initial curve is right here, the slowest one. Then we've got 1.5 times that function, 2 times that function. And it certainly appears to me that this curve is twice as tall as the curve we have on the bottom. There's 3 times as tall, and there's a curve that is stretched out to 4 times the original curve. So we are seeing the same thing happening. Okay, going back and making some changes to my equations. I'm going to go back to the original function, square root of 4 minus x squared. And then this time, instead of multiplying by 1.5, oops, let's see, I'll have function y1 of half of, sorry. Instead of multiplying by 1.5, I want to multiply by 1/2, so 0.5 times the equation that's in y1 of x. And then I'll have 1/3. So depending on which calculator you're using, I want to find a fraction. Yeah, I'm working in the wrong mode. So we'll do this the old-fashioned way. Open parenthesis, 1 divided by 3, close parenthesis, times the function y1 of x. And then we'll have 1 divided by 4 times the function in y1 of x. And I've only got 4 equations. So now we're looking at what happens to the graph if we multiply by 1/2 or 1/3 or 1/4. Notice that these coefficients are all numbers that are less than 1. I also need to change my viewing window. My x's are okay, but I want to change my y values to -0.5 and 2.6. So there's the initial curve. There's 1/2 times the first function, 1/3 times the first function, and 1/4 times the first function. So each one of those is getting shorter. So we're shrinking the graph down. So what I see is a vertical shrink. The first one is 1/2 as tall, so we're shrinking by a factor of 1/2, 1/3, or 1/4. Another way of talking about that is a vertical compression. So where you're squishing or compressing the graph. So we want to check and see if we have the same relationship if we change our first function to the square root of x plus 1. So there's the square root of x plus 1, and then 1/2 times the square root of x plus 1, 1/3 times the square root of x plus 1, and 1/4 times the square root of x plus 1. So our first function is 1/2 square root of x plus 1, 1/3 square root of x plus 1, and 1/4 square root of x plus 1. Hope you guys are more successful in squeezing in your writing on the lines there. So I think we do see the same changes. So to summarize this, let me make that a little bigger. Number 18, part A. If C is a number greater than 1, and we multiply that number bigger than 1 times the function f of x, that vertically stretches our graph by multiplying all of our y coordinates by c. So if you multiply by a number bigger than 1, it gets bigger. If c is a number between 0 and 1, so it's less than 1, then multiplying each of your y values by that number less than 1 is going to make it shorter, smaller, so this shrinks the graph by c.